In this video, we'll be talking about how we can understand the importance of buffers in chemical systems through practical examples. In chemical systems, especially in industrial or biological contexts, the addition of acid or base to a substance can interfere with important chemical reactions. Some examples of this might be excess hydronium ions reacting with a chemical agent to produce unwanted products, or a biological reaction such as photosynthesis being unable to occur above a certain pH level. Sometimes we want to be able to add an acidic or basic reagent without interfering with the overall pH of the system. Fortunately, we can make use of our understanding of how acids and bases work to create a buffer to control the overall pH of our chemical system. So how can we make a buffer? We start by adding a weak acid and its conjugate base, or a weak base and its conjugate acid. This is usually done in practice by adding a weak acid, such as ethanoic acid, phosphoric acid, or sometimes sulfuric acid, and adding in a weak conjugate base made up from the salt formed by the ionized form of that acid. We end up with something like this equilibrium system here for ethanoic acid. On the left-hand side of the equation, we can see that the weak acid is reacting with the water to produce hydronium ions and the negatively charged ionic form of that acid. This works in an equilibrium system which can react dynamically to the addition of excess hydronium or hydroxide ions. This is usually done in practice by adding a high concentration of an easily formed weak acid, such as phosphoric, carbonic, or ethanoic acid, and adding some kind of salt formed with its negatively charged ion, such as sodium carbonate, which will dissociate in the solution. We end up with something like this equilibrium system here. On the left-hand side of the equation, the weak acid is reacting with the water to produce hydronium and ethanoate ions as product. Competing with this, on the right side of the equation, the hydronium ions and the ethanoate are producing water and ethanoic acid as products. Eventually, this system will reach an equilibrium. Notice that had we added a strong acid, like hydrochloric acid, then we would not have this equilibrium system forming. The reason for this is because strong acids ionize completely in solution, which would not form the equilibrium system that we see here. We know from our previous study on equilibria that when the concentration of the products increases, the system reacts to favor the reactants. And similarly, when the concentration of the reactants increases, the equilibrium shifts to favor the products. What does this mean for our reaction? Well, suppose we had an increased concentration of hydronium ions in the solution, formed by some strong acid ionizing, such as hydrochloric acid or sulfuric acid. What would happen? Well, we know that since we have an increased number of reactant in this equilibrium equation, the equilibrium will shift to favor the products. In the reverse reaction, we see that most of the hydronium ions become consumed, reproducing the ionic form of ethanoic acid. In short, we are counteracting the addition of excess hydronium ions in the reverse reaction by consuming them. Similarly, had we added some strong base, like sodium hydroxide, we would observe a decreased concentration in hydronium ions. This is because the hydronium ions would react with the hydroxide in the base to reproduce water. Because of this, our equilibrium system will now shift to the right to favor the products, and some of the hydronium ions would be restored. This would counteract the change in pH that would otherwise be brought on by adding strong base. This works great most of the time, but what if we try to break our buffer system by adding excess strong acid or strong base? This brings up a concept known as buffer capacity. Let's say we added so much excess acid that we tried to overwhelm this system. Remember, the only reason why the hydronium ions can reform into the unionized weak acid is because of the presence of the ethanoate ions. So, if we completely exhaust this reaction by consuming all of our ethanoate ions in the reverse reaction, then we will not be able to neutralize any more incoming hydronium ions. This is because we have run out of reactant to consume in the reaction. So the pH of the system would radically drop. We'd see the pH follow a curve a little bit like this. When we add so much strong acid, so much so that we consume all of our product in the reverse reaction, we would notice the pH of the system radically drop, as if we had added acid to a solution not containing a buffer. Similarly, had we added a lot of strong base, so much so to exceed the capacity of the buffer, the pH of the system would radically rise. Often we want to keep this flat part of the curve where we can add acid or base without changing the pH for as long as possible. This is known as the capacity of the buffer. The main way we can assure a suitable buffer capacity is by ensuring a high concentration of the weak acid and conjugate weak base, or weak base and conjugate weak acid, so that we can have many reverse reactions or forward reactions occur to stabilize the system. Biological reactions can usually only occur in a system where the pH is tightly controlled. Blood is a great example of this. Blood must be maintained in a very specific pH window of only 7.35 to 7.45. Diseases entering the body or health conditions can cause the pH of the blood to rise or drop by preventing natural acid-base reactions in the body. These processes are called alkalosis or acidiosis, respectively, and can potentially be fatal. For example, diabetes, if left untreated, can prevent natural reactions in the blood involving sugars. If not for buffer systems in the blood, day-to-day reactions occurring can potentially be fatal. For example, respiration in cells converts oxygen into carbon dioxide, which then absorbs into the bloodstream. The carbon dioxide then reacts with the water in the blood to form carbonic acid, which in turn ionizes into hydronium ions and hydrogen carbonate, its weak conjugate base. Fortunately, the phosphate buffer system responds to this change by neutralizing some of the added hydronium ions. We notice in this equilibrium equation that an increased concentration of hydronium ions would lead to the reverse reaction occurring in this equilibrium system. This reverse reaction reacts the hydronium ions with the dihydrogen phosphate. This produces the unionized form of the acid. This helps keep the pH of the system constant until the carbon dioxide can be dispelled from the body. If this buffer system didn't exist, then the pH of our blood could fall as low as 4. A pH this low would make it very difficult to synthesize proteins in cells and could lead to the deaths of important cell organelles. Fortunately, the relatively high concentration of these dihydrogen phosphate ions of roughly 0.09 mol per liter helps to maintain a high buffer capacity. Therefore, these sorts of changes never usually occur in the body. Let's have a look at this question to test our understanding. During hyperventilation, humans expel more carbon dioxide from their bodies than normal in respiration. How does the pH of blood change in hyperventilation, and how does the phosphate buffer system respond? If you like, you can pause the video and give this question a think through by yourself. This is a tricky question because we actually have more than one equilibrium systems at play here. First note that dispelling carbon dioxide from our body will lead to a decreased concentration of carbon dioxide in the bloodstream. Therefore, our first equilibrium system will shift to the left to favour the products. This in turn will lead to a decreased concentration of carbonic acid as it is consumed in the reaction. This in turn affects our second equilibrium system. The renewed decreased concentration of carbonic acid will cause this equilibrium system to react. The decreased concentration of reactants in this equilibrium system will cause the system to shift to the left to favour the reactants. This in turn will lead to a decreased concentration of hydronium ions when they are consumed in the reverse reaction. The decreased hydronium ions would make the blood much more alkaline. Fortunately, the phosphate buffer system will respond to this change. The decreased concentration of hydronium ions will then cause this equilibrium system to shift to the right to favour the products. This then restores the lost concentration of hydronium ions, keeping the pH of the blood constant. Buffers are useful in many chemical systems as a means of controlling pH. Blood and respiration is just one example of this. Buffers are also useful in other chemical systems such as fermentation, agriculture, and other biological reactions. I hope this video has helped us learn something more about buffers and how they are used in chemical systems. Thank you for watching. My name is Henry, part of a team at Elucidate, a non-profit organisation that helps young people succeed at school. If you would like to see more chemistry videos, click up here. If you would like to learn more about us or support us, click down here.